Plastic to fuel conversion involves breaking down polymers into shorter hydrocarbon chains. Distillation is a method used to convert plastic into fuel. The distillation process yields hydrocarbons suitable for use as fuel. Polymers in plastic are long chains of repeating units. Shorter hydrocarbon chains are more volatile and can be used as fuel. A distillation apparatus is essential, comprising a retort or flask, a condenser, and a collection vessel. A heat source, such as a heating mantle or burner, is required to vaporize the liquid. A thermometer is used to monitor the temperature of the vapor during distillation. Safety gear, including gloves, goggles, and a lab coat, is crucial for protection during the distillation process. Polyethylene, PE, polypropylene, PP, and polystyrene, PS, are suitable plastics for distillation processes. Polyvinyl chloride, PVC, and polyethylene terephthalate, PET, are not suitable for distillation due to their chemical properties. Proper sorting of plastic waste is crucial for effective distillation. Cleaning plastic waste before distillation is essential to remove contaminants. Distillation of improperly sorted or cleaned plastics can lead to unwanted byproducts and reduced efficiency. The chemical structures of suitable plastics allow for easier breakdown during distillation. Plastic materials are prepared by shredding or cutting them into smaller pieces. Uniform plastic piece size ensures even heating during the distillation process. Consistent particle size promotes efficient breakdown of plastic polymers during distillation. Proper plastic preparation enhances the overall efficiency of the distillation process. The goal of plastic preparation is to optimize the conditions for subsequent processing. The distillation apparatus is assembled step by step to ensure proper functionality. The retort is connected to the condenser as a primary step in the distillation process. Airtight joints are crucial to prevent vapor leakage during distillation. Preventing vapor leakage ensures effective separation and collection of the desired distillate. Accurate thermometer placement is crucial for monitoring vapor temperature during distillation. The thermometer measures the temperature of the rising vapors, indicating the boiling point of each fraction. Different hydrocarbon fractions vaporize and condense at distinct temperature ranges. Monitoring temperature allows for the selective collection of desired fuel fractions. Precise temperature control ensures the purity and yield of each distilled fraction. Distillation separates mixtures based on differences in boiling points, enabling the isolation of specific components. The plastic within the retort undergoes a gradual heating process. As temperature increases, the plastic begins to melt and transition into a semi-liquid state. Continued heating causes the molten plastic to vaporize, releasing gaseous compounds. The vaporization process converts the solid plastic into gaseous components within the heated retort. Vapor travels through the condenser in a vapor collection system. The condenser facilitates cooling of the vapor. Cooling causes the vapor to condense back into liquid form. The condensed liquid is collected at the outlet of the condenser. Condensation is a phase transition from a gaseous state to a liquid state. Efficient condensation maximizes liquid recovery in vapor collection processes. Condensed liquid fuel is collected in a designated vessel. Temperature monitoring is crucial during the condensation process. Different fuel fractions condense at varying temperatures. The collection vessel is designed to prevent contamination of the condensed fuel. Real-time data analysis provides insights into the efficiency of the condensation process. Precise temperature control ensures optimal separation of fuel fractions. Fuel type production is directly related to temperature control during the refining process. Specific temperature ranges are required to produce gasoline, kerosene, and diesel. Precise temperature monitoring ensures the correct fuel type is produced. Deviations from optimal temperatures can result in incorrect fuel production. Fractional distillation separates fuel components based on their different boiling points. The process involves heating the fuel mixture to vaporize its components. As the vapor ascends, different fuel fractions condense at varying temperatures. Specific fuel types are isolated as they condense and are collected separately. Fractional distillation allows for the efficient separation and collection of various fuel fractions. Fuel flammability is a key property assessed during basic fuel testing. Fuel density is measured to ensure it meets required specifications. Distilled fuel characteristics are compared to standard fuel benchmarks. Testing ensures the produced fuel meets safety and performance standards. Fuel properties like flammability and density are critical for proper engine operation. Appropriate safety gear is essential for preventing workplace injuries. Proper ventilation systems mitigate the risk of inhaling harmful fumes and vapors. Flammable materials must be handled with extreme caution to prevent accidental fires. Open flames should be strictly prohibited near plastic vapors due to the risk of ignition. Adherence to safety protocols minimizes risks associated with hazardous materials. A slow distillation process may indicate insufficient heating of the distillation flask. To address a slow distillation, verify the heating mantle is functioning correctly and is properly coupled with the flask. Ineffective condenser cooling can result in vapor escaping instead of condensing into liquid. Ensure adequate cooling by checking the condenser's water flow rate and temperature. Leaks in the distillation apparatus can lead to loss of product and potential safety hazards. Inspect all connections and joints for leaks and use appropriate sealing methods to ensure a closed system. Plastic to fuel conversion reduces plastic waste by transforming it into a valuable energy resource. Converting plastic to fuel conserves fossil fuels by providing an alternative energy source. Plastic to fuel technology minimizes landfill space by diverting plastic waste from landfills. This conversion process mitigates environmental pollution associated with traditional plastic disposal methods. Plastic to fuel conversion offers a sustainable solution for managing plastic waste and promoting energy independence. Plastic to fuel distillation offers a sustainable approach to waste management by converting plastic waste into usable fuel. The distillation process involves heating plastic waste in an oxygen-free environment to break down polymers into shorter hydrocarbon chains. Catalytic cracking enhances the efficiency of the distillation process by using catalysts to accelerate the breakdown of plastic polymers. The resulting hydrocarbons are separated through fractional distillation into various fuel types, such as gasoline, diesel, and kerosene. Further research and development are essential to optimize the plastic-to-fuel distillation process and enhance its economic viability and environmental benefits.